Hi guys, I welcome you all to my YouTube channel. So in this video I am going to discuss about one important theorem called Castigliano'S Theorem. So this question is from your strength of material subject. Okay, the question is a steel bar having inside and outside diameter of 160 mm respectively is bent to the form of a quadrant of 2 meter radius as shown in the figure. So the vertical deflection at the free end under the given load. Okay, so Young's modulus is given as 200 gigapascal. So see here, so this is the bar, and remember this bar is not a solid bar. It is not a solid bar. This is not a solid bar. This is a hollow bar. Hollow bar, because here inside and outside diameter are given. Okay, so according to the Castigliano's theorem, so before telling about Castigliano's theorem, let me show you the situation after applying the load. Okay, so after application of the load, the situation will be like this type. So when you apply the load P, so the bar will bend in the form of almost like this. Okay, so this small deflection is called your delta. Okay, now according to Castigliano's theorem, this delta deflection at the point of application of the load is exactly equal to differentiation of strain energy. U is called strain energy with respect to your load P. Okay, differentiation of strain energy with respect to the applied load will give you deflection at the point of application of the load. Now the important thing is that to find strain energy in this situation, you will not be having much amount of time in competitive examination. So I already solved lots of problem depending based on your Castigliano's theorem. Now I want you to remember a single formula, that is del V for vertical. Del V is equal to P R cube by 2 EI into pi by 2. Okay, so this single formula will help you to solve this entire question. And del V means this is the vertical. For vertical deflection, this formula is important. Okay, so you do not need to find strain energy here. You just apply this formula. And for horizontal deflection, the formula is PR cube by 2 EI. Just remember this formula. Okay, now if you apply this formula here, equal to P is given as 1 kilonewton, so 1 kilonewton, that is 1000 newton, and R is given as 2 meter. Okay, let me convert all these units into mm. So meter means 2000 cube, right? PR cube divided by 2E. E is 200 GPa. So if you write in terms of millimeter, so it will be 200 into 10 cube. 200 into 10 cube, and this is I, right? So moment of inertia in case of hollow cylindrical bar, is given by pi into outer diameter power 4, inner diameter power 4 divided by 64. So you can find this I value, right? And this is the I, and entire thing will be multiplied by pi by 2. So if you put this I hollow value here, so answer will come as 7.35 mm. So this is the final answer. See, if you go in the derivation, that is strain energy with respect to the loading. So it will consume your lot of time, because to find strain energy here you have to consider one small angular portion. Suppose if this angle you take as theta, then this small angle will be your d theta, and this is given as r. So if you find strain energy is given by m square dx divided by 2ei. So this is the formula for your strain energy, and again m will replace by p into this distance, because load is applying in this direction, and distance from the fixed end will be your r sin theta, right? Because this will be r cos theta, and this is your r sin theta. So p into this distance r sin theta, this will be your moment, right? So m square, and dx will be replaced by r d theta divided by 2ei. So this will be your strain energy, and you have to differentiate this entire term with respect to your loading, that is p. So it will consume your lot of time in your competitive examination. So I want you to remember just this formula, and you can apply in examination, and you can find the answer within 1 or 2 minutes. Okay, so I hope this was helpful to you, and I will upload one more video based on your Castigliano's theorem. So it will be better to understand the concept. Thank you.